Okay, everyone, continuing on, let's talk about a complex number. So what we just talked about before was imaginary numbers, and we said anything with an I in it, right, would be imaginary. So when you're taking the square root of a negative number, that's what gives you an imaginary number. A complex number is a combination of a real number and an imaginary number together. So if you think of real numbers, right, your real numbers would be like integers. 12, 0, -5, things like that. Real numbers would also be radicals. So for example, if I had square root of 2, or if I had square root of 16, or if I had pi, right? Those are all real numbers. Fractions are real numbers. I could have 3 halves. I could have, lots of different things there as well, okay? However, when we're talking about imaginary numbers, those are things that have I in them. So I could have 7i, that's an imaginary number. I could have 4/3 I, that's an imaginary number. I could have it as a decimal, 1.2 I, that's imaginary. I could have I radical 6, it's imaginary. I could have negative I radical 3. I could have 2i radical 11. Okay, all of those are different examples of imaginary numbers. So a complex number has a real component to it and an imaginary component to it. So think of it as you're bringing the two of them together. So an example of a complex number would be 5 plus 2i. Okay, that's a complex number, because it has a real component to it and an imaginary component to it. And actually, all numbers that you've ever worked with have all been complex numbers. You just didn't know it, right? The number 2 is real. You could say it as 2 plus 0i, but you're never going to say that. You're never going to walk into McDonald's and go, "Can I have 2 plus 0i hamburgers?" Right? You'd sound ridiculous. They'd laugh at you probably, or whatever, because A, they wouldn't know what you're talking about, and B, we just don't talk like that, okay? But every number in the universe is actually a complex number. Every number has a real component to it and an imaginary component to it. So maybe I just blew your mind a little bit with that, I'm not sure. But that's the idea behind what a complex number is. And when we talk in general forms, we say A plus BI, where A is that real component and B is that coefficient in front of your I term. And so this is in general form of a complex number. So you'll see, write it in A plus BI form. You'll see that those directions in problems sometimes. When they say A plus BI form, that just means to write it as a complex number. And just for notation purposes, you always put the real component before the imaginary component. Okay, we would not write this as 2i plus 5. We always put the real component first. Okay, so let's talk about figuring some of these types of problems out. When we talk about equating complex numbers, we're taking a real number and a imaginary number, putting it together, right? So if I said, okay, remember A plus BI form, and I said, well, here's my complex number, 8 plus 10i. So I said, well, what is your A value and what is your B value? Okay, your A value is just this first part here, right? This is your A and this is your B. So in this example, A would be 8 and B would be 10. Now notice I don't write I here because A and B just represent the numbers. Okay. Likewise, I could give you a problem. I could give you 1/3 minus 5/3 I. And I could again ask you what is A and what is B. So in this case, right, here's your A and here's your B. So you would say A is 1/3, and you would say B is negative 5/3. Okay, so that's the idea between what a complex number is and how you would write it. Sometimes they get pretty complex too. I'm not meaning to use that word again, but let's say I gave you this. X plus 2 plus x plus 7i. Okay, then again, your a value is this real component here. This is your a, and this part is your b. Okay, so in this case, your a would be x plus 2, and your b would be x plus 7. So lots of different ways they can ask those types of problems. So let's look at this. Clearly, once again, it didn't translate over, so I'm going to scribble this out, and I will rewrite the problem. So let's not worry about this because this is a big yucky poo right there. Okay, so our problem was this. 3x minus 5i is equal to 6 minus 10yi. And what they're asking us to do is to find x and y. Okay, that's what it says up here, find x and y. So remember, when a complex number, we have a plus bi, right? Here's a plus bi, here a plus bi, and here's a plus bi. And this equal sign here tells me that my a values have to equal each other and my b values have to equal each other. So my a value on this side is 3x, my a value on this side is 6. So 3x equals 6, which means that x has to be 2. Okay, so that's all they're asking you to do there. Let's look at the y values. I have negative 5 here, and I have negative 10y here. So I have negative 5 is equal to negative 10y. And so when I solve that, I end up with negative 5 over negative 10 is y, and that reduces to 1/2. Okay, so those are my x and y values. That's how you find them. Just set your a values equal to each other and your b values equal to each other and solve those. All right, so let's talk about finding the zeros of a function. And to do that, let me scribble this out again. I don't know why it does that. I'll just have to make a mental note not to preload the problem in there. So here's our problem. We have f of x is equal to x squared minus 2x plus 5. Okay, so in order to find the zeros, the first thing I have to do is set it equal to 0. So I'm going to go through the process of solving this, and I'm going to solve it by completing the square. So here's just a quick review of completing the square. You move your constant term over to the other side. You're going to take half of this middle term and then square it. So half of negative 2 is negative 1. If I square negative 1, I get positive 1. Whatever you add to one side of the equation, you have to add to the other. When I factor this out, I end up with x minus 1 squared is equal to negative 4. Again, I'm going to just keep solving it. I'm taking the square root of both sides, and that leaves me with x minus 1 on this side. That leaves me with plus or minus the square root of negative 4 on this side. Bring it up here. So I have x minus 1 is equal to plus or minus. I know I'm going to have an I in here. I times the square root of 4. The square root of 4 is 2, so that gives me plus or minus 2i. Add 1 to both sides, you end up with 1 plus or minus 2i. Those are your two roots. You will always have two roots when you're solving a quadratic equation. Okay, so 1 plus 2i is one root, 1 minus 2i is my other root. Okay, let's look at the next one here. Same idea, we're going to go through and solve it. and it will not be that big mess. It'll be this. G of x is equal to x squared plus 10x plus 35. Okay, again, I'm going to set it equal to 0 and plus 35 equals 0. And then I'm going to go ahead and move my constant term over to the other side. And from there, I'm going to take half of that middle term. Half of 10 would be 5, and I'm going to square that. That would be 25. Make sure you add that to both sides. 25. Here you end up then with x plus 5. Oops, 5 squared is equal to negative 10. I'm just going to go up here where I have a little more room. Then I have, I'm just going to rewrite it first. X plus 5 squared is equal to negative 10. I'm going to go ahead and take the square root of both sides. Oops, square root. On this side then I'm left with x plus 5, and here I have plus or minus the square root of negative 10. Remember that because I have that negative there, that gives me an I out in front, so I have plus or minus I radical 10. And so when I solve this, I get x equals negative 5, because I have to subtract 5 from both sides, plus or minus I square root of 10. And those are my two complex roots, negative 5 plus or minus I square root of 10. Now, the reason that we have these roots, and we're talking about zeros, and remember that when we were talking about zeros before, we said, well, when we graph that parabola, wherever it crosses the x-axis are our zeros. With these particular functions, they never actually cross the x-axis, which means that they don't have any real solutions, because this x-axis is all real numbers, right? We have integers, we have fractions, positives, and negatives on that x-axis. But what happens with these graphs is they're either entirely above the x-axis, so they never cross it, or maybe they're entirely below the x-axis, so they never cross it. So they still have solutions, but they're imaginary because they don't cross the x-axis. So that's what those graphs would look like. Okay, real quick, one last thing I want to talk about are complex conjugates. Every complex number has a conjugate. And all it is this: if I gave you the complex number 2 plus 5i, its conjugate is 2 minus 5i. If I gave you 3 minus 7i, its conjugate is 3 plus 7i. The only thing that's happening here is that the sign between them is changing. So if it was plus, it becomes minus. If it was minus, it becomes plus. We'll get into more with conjugates as we move forward, but that's what a conjugate is. I think there are a couple of homework problems that ask you that. So only change the sign between them, and that's all you have to do for the conjugate. And that's pretty much everything for now with complex numbers. Like I said, we're going to get more involved with them, and we will get into some other things. Similarly, real quick, if you have a complex number that starts with 0, so if I had 0 plus 8i, the conjugate of that would just be 0 minus 8i. So sometimes if you just see the imaginary number written, so if you just see 10i and it asks for the conjugate, it just becomes negative 10i, and vice versa. If I start with negative 15i, the conjugate would be positive 15i. So just a quick little glimpse into conjugates, and then also we went through how to find complex zeros or complex roots in quadratic functions. Okay, hope that helps. See y'all in class next time. Take care, everybody.